We ended yesterday in our shortened period talking about calculating rates of reaction, how we can talk about the average rate over a period of time. And to do that, you're basically just taking the graph, finding the point at that time, and calculating the rate between the beginning and the end, or for that period of time. So you're just finding the points on the curve, and you're doing change in y over change in x. So you're basically just finding the average slope during that time period. You can also find the rate of reaction by drawing a tangent line to the curve at a particular point. And that is the slope of that line is going to be the reaction rate at that moment in the reaction. So you can see that the reaction rate starts out with a pretty steep slope, and that slope, as we continue, ends up getting shallower and shallower and shallower. And it doesn't matter whether we're looking at it from the perspective of the decline of reactants or the increase in products. Either way, we can draw that slope. That it's going to be the negative. The rate is going to be the negative of the slope for this type of graph, and the positive of the slope for the product formation graph. So when you draw a tangent line, that is just a straight line that intersects a curve at one point. So you're going to find the point on the curve that corresponds to the time that they're asking for. For example, the instantaneous rate here at 60 seconds would be this point right here. You would draw a straight line so that it just touches the curve at that point. All right, and you're not going to be perfect, and that's okay. When they ask you to do something like this, they will accept a range of answers depending on where exactly you drew that line. I recommend taking your answer sheet and using that as a straight edge if you're asked to do something like this on the test. So as long as it is reasonable, as long as it hits the line, the curve at one point, and is reasonably close to the slope of what the tangent line would be, you're good. Okay. So either one of they may ask for either one of those. They may ask how you would find one of them. They may ask you to describe the process of finding it. There's lots of different ways they could ask you about this. But that is the basics of calculating the rate of reaction from a graph. And again, this is the same idea, but we're looking at the product curve. And again, we have a very steep slope to start, and then slowly the rate of reaction decreases. And that is because as we go through the reaction, we are running out of our reactants, right? The concentration of reactants is getting lower and lower and lower. We just don't have as many particles to react. So the rate of the reaction is going to slow down. Okay. So this is an example from your study guide of a kind of situation where they might show you a plot, or they might ask you to make the plot or complete a plot. And then they might ask you, what's the rate at a particular time point, or what is the average rate? So if we're looking at the rate of formation at 40 seconds, we're going to find, okay, here's 40 seconds on the x-axis, and I'm going to find where that intersects the curve. That is at this spot right here, at this point. So I'm going to draw a line that just barely touches that curve, a straight line, and I'm not going to be able to do it on here because I can't really use a ruler on the board, but something like that. Maybe you would choose a slightly different angle than what I chose. Hopefully you'll draw a better straight line than I did, but when you're actually doing it on paper. But it's within a range. And then once you have that line, you can say, okay, let's find some points on that line that I can use to define that line, right? So here, I might pick a point right here. No, not that. Say here, and then I might pick a point, say right here, and I might call this point, you're going to have to estimate, right? So this might be 20, 40, and this might be 50, And then I might call that 55.5. I don't know. You know, you don't have to get too lost in the weeds of exactly where the point is. Try to pick a spot where you can identify a point, you know, but it doesn't matter where on the line the points are. You just pick 2 points that you can identify, and then you're going to do exactly the same thing you do with the average. You're just taking the slope of the line, which is going to be change in y over change in x. So I'm going to say 55.5 minus 40 divided by 50 minus 20, and that's going to give me my slope, okay? And that's going to be in centimeters cubed per second, right? So that's how you would do that kind of calculation if you were asked to do it. Let's skip that. There are several ways of measuring the rates of reaction, and some of you have either seen other people doing them as an IA, or maybe you've done it yourself. One possibility is to, especially if you have something that produces a gas, you can measure that in a number of different ways. For example, you can measure mass loss. We had some students doing reactions that produced gas, and they measured mass loss. Binta was one of those people, so she did a reaction that produced gas, and she tracked the mass over time. And so you can look at, and you're making the assumption that the mass lost is equal to the amount of gas being produced, right? And so you can plot it really either way, as mass lost, or you can plot it as grams of CO2 produced, or O2, whatever it is that it's being produced. And when you have those data, you can look at the reaction under different conditions, and you can say, okay, here's my mass over time, and I might have 2 different conditions, different temperatures, different concentrations, different particle size, things like that might change the reaction rate, and you can plot them together on one graph and see visually the differences between them, okay? Other things you can use to measure reaction rates are pH, or conductivity, ion concentration. You can measure how long it takes for a precipitate to form, or how long it takes for something to change color. So when he was doing the iodine clock reaction, so she had 1 data point for each trial. Unlike Binta, who had multiple data points for each trial, the reaction only changes color once. Or in the case of the disappearing cross that we saw a sample IA for, the cross only disappears once. So then you have 1 data point for your for each trial. But then you can graph it no longer as concentration or amount of reactant or product versus time, but you have a data point for each condition. So maybe you're changing the temperature, and at each temperature, you have a different data point of how long it takes for the reaction to happen. Or you might have concentration on the x-axis. You do things with a different concentration of one of your reactants, and you see an effect on the time that it takes to reach that endpoint, whatever that endpoint is for your reaction. So these are all things that can be done with reaction rates. You can also measure using a titration. A lot of times, if you have a reaction that's going over time, you can temporarily halt it by putting it in an ice bath, and then you can take a sample and titrate how much acid or base is present, or how much of your redox oxidized, the thing that's being oxidized or reduced is present, and then continue the reaction for longer. So you would basically take samples at different times and either titrate or measure whatever it is that you need to measure at some point. A couple of years ago, Roger did this where he was doing a reaction of copper and brass, nitric acid and brass, and he couldn't do the reaction in a cuvette in the spectrophotometer because the reaction produces poisonous gas. So he had to do the reaction in the hood, but then he could take samples of his reaction, the reaction mixture, and dilute them and put them in the spectrophotometer and see like how the color was changing over time of the copper. So that's another thing you can do. All right, and the last thing we need to talk about is what things can affect the rates of reaction. So there are several things that are sort of standard things that you need to know about that they can have an effect and what direction the effect is going to be in, okay, and why. So this is starts on page 9 of your study guide with these different things. They might not be in the same order that I have them in the slides. First one is temperature, okay? Increased temperature increases the rate of the reaction, right? This is kind of an intuitive thing. You heat something up, it goes faster. But what you need to know about temperature is that it actually has 2 effects on the reaction rate. One of them is that if the particles are moving faster, they're going to collide with each other more often. So you're going to see a higher frequency of collisions. Now, it's important because sometimes the mark scheme is annoying for these questions, and they don't accept more collisions. They accept a higher frequency or probability of collisions. So if you are asked a question about that in this paper 2, make sure that you're using the term frequency or the term probability. It's more likely that particles are going to collide if they're all moving faster. Okay. But also, the second thing that temperature has an effect on is the effectiveness of those collisions. Because at higher temperatures, you're going to have more particles. Remember your Maxwell-Boltzmann distribution. You're going to have more particles above the activation energy threshold. So if we increase the temperature, we're going to have more particles that are capable of having an effective reaction when they do collide. Okay? So that's 2 things that temperature does, is frequency of collisions and the energy of those collisions. Okay. Concentration is another one that a number of people tested the effects of. Haiti did this with different concentrations of sodium hydroxide on the rate of bleaching of a dye. And could see a big difference between all the different concentrations that she had and how quickly that dye was turned colorless. In most cases, when we're talking about these reactions, we're talking about something that's happening in a solution. And so increasing the concentration of the solution is going to increase the frequency of those collisions. Okay, the more particles we have, the more likely they are to collide. Okay. I put up here of the limiting reactant, and we will circle back around to that. I know some of you did look that up in your study guides and start work on that worksheet that I gave you a long time ago, but that we didn't actually get to. Some of you did not. That's okay. I didn't ask you to do it on your own. But we'll circle back around to that. But in any reaction, it's rare that you have the exact, and in some ways really philosophically impossible to have the exact number of particles to have the exact molar ratio of your reactants correct. All right, so that everything is going to react exactly the way it says in the chemical equation. Usually you have a whole bunch of something and then some of something else. The thing that you have a whole bunch of is going to still be there at the end of the reaction because you're not going to use all of it up. The stuff that you don't have much of is your limiting reactant. That's going to determine how much of the reaction can happen. So when you're doing the vitamin C titrations, the amount of vitamin C is your limiting reactant because as soon as that gets used up, the reaction system moves on to react with the starch and you get the color change. So you can still have an effect of changing the concentration of the reactant that's in excess, the one that we already have a ton of, but it's going to be a much smaller effect than changing the concentration of the limiting reactant. We actually had a student who did that for an IA and pretty much changed the concentration of the excess reactant and really didn't see a whole lot of difference between the different conditions. And that was why. So that's important. So this is like when you're talking about something in solution, the concentration of a solution, the molar concentration, moles per liter, moles per decimeter cubed. is going to be an important factor. The same thing happens when we have gases. If we put a bunch of gases in a tank and have them react, the same thing happens, but we don't talk about it in terms of concentration of the gas. We talk about it in terms of the pressure of the gas. But it's the same concept. If we have more particles within the same amount of space, or if we have a smaller, same number of particles but a smaller space, they're going to be more concentrated. They're going to be more of them next to each other, more of them able to collide with each other. Okay, so it's the same concept. The pressure's effect on reaction rate is exactly the same as concentration effect. It's just looking at it from a different perspective. Instead of particles in the solution, we're talking about gas particles in the space, in the reaction space. Okay. This is just a picture of how, something under low pressure, if you then increase the pressure, make the space smaller, then you're increasing the frequency of collisions. And the last, not quite the last thing. The next thing is particle size. So think about having, say you're doing what Patrick was doing, which is reacting chunks of marble in acid, okay? And he's got a particular size chunk of marble. And the acid molecules can only collide with the outside. They're not going to be able to hit the molecule or the ions on the inside of the chunk, right? That's the only thing that's available is the outside. And so if we can then take that chunk and cut it in half, now all of a sudden we have these inside faces of the chunk that are now open to reaction. So we've increased the surface area by making the particle size smaller. Every time we do that, we increase the surface area. This is why Binta putting an entire Alka-Seltzer tablet in with water or acid takes longer than when some of the other folks in first period were doing the same reaction with powdered chemicals. All right, that was a much faster reaction because the water, the acid, whatever they were using was much more able to access, the reactants were able to access each other more easily because they were in powder form, okay? So surface area matters. One of the things Patrick did is we used these progressive sieves to try to get all of his marble chips to be about the same size. So they were big enough to fit through one sieve, but small enough to big enough to be stopped at one sieve, but small enough to go through the one before it. So it's like within a range. And so that's something that you can try to do to regulate particle size. But the bigger the particles, the smaller the surface area and the slower the reaction. If you have smaller particles, same mass of the substance, smaller particles, vastly increases the surface area, increases the rate of reaction. Okay. This is just another picture of the same thing. Okay, so we have temperature, concentration or pressure, particle size, and then of course we talked earlier about a catalyst having an effect by lowering the activation energy. So those are the four main things that can affect the rate of the reaction. Okay. All right, I think that is where, that's where we're going to stop on this one. Anybody have any questions about the stuff we've talked about with kinetics and reaction rates? Anything that, I know it's a whirlwind tour. It's what we got to do. All right. So let's move over to topic 5, which is energetics. We've covered some of this in honors chemistry. You may or may not remember it. Hopefully some of it will look at least vaguely familiar. When we're talking about energetics of reactions in general, we're talking about temperature, we're talking about heat. Heat is basically the movement, the transfer of energy from one object to another, from one system to another, between the system and the surroundings. It's always going to flow from the warmer object to the colder object until they are both at the same temperature, at which point the heat stops because there's no more movement of energy. Okay, all the energy has been equalized. Now, that's not to say there's not any more heat. There's still movement between particles within the objects, because we know that some of them are moving faster than others, and as they collide, they transfer some of that energy. And so there's a whole bunch of things going on within the substance. But when we're measuring the transfer of heat, we're talking about going from a warmer object or system to a colder one. We've already talked about temperature being the average kinetic energy. I did want to mention that we do use Celsius, but more in science we use Kelvin, which is just another scale for temperature. It's actually very similar to Celsius. The scale is exactly the same in that 1 Kelvin is the same, like a difference of 1 Kelvin is the same as a difference of 1 degree Celsius. However, the Kelvin scale goes from absolute 0. So 0 Kelvin is absolutely no movement. Okay? We have not yet achieved that in a laboratory. We've come close. All right, but that's kind of a theoretical thing. The way that we got there is from Lord Kelvin doing these experiments with gases where he looked at decreasing the temperature and looking at the effects on pressure and volume. And he found that for the same amount of gas, you had this nice linear relationship. And so what he was able to do was basically say, okay, let's take the lines of data that I can capture, and then let's extrapolate it back to the coldest temperature that I can't do. And they all converge at this point at 0 Kelvin, which is negative 273.15 Celsius. That conversion is in your data booklet on section 1 or 2. So because that's an absolute scale and not a relative scale, that's what we use in science. A relative scale is like Celsius is pegged so that 0 degrees is the freezing point of water and 100 degrees is the boiling point of water. So it's relative to the phase changes of water at normal atmospheric pressure. Whereas this is, to some extent, independent of that. Okay, it goes to an absolute number. So anytime you're looking at an absolute temperature reading, you're gonna, if it's in Celsius, you're gonna add 273.15 to make it into Kelvin. All right. If you are, like I said, the scales are exactly the same. So if you're looking at a change in temperature from like beginning to the experiment to the end, so you're subtracting them, that change in temperature is going to be the same regardless of Celsius or Kelvin, because the difference between degrees is exactly the same. So if you're looking at change in temperature, it doesn't matter. You don't have to convert it. Okay. We've already talked about the Maxwell-Boltzmann distribution. So distribution of the kinetic energy of any given particle, how many of them are at different temperatures. We talked about how the distribution has a peak, and then it has a long tail on the higher energy side. So it's not totally symmetrical. It also should not touch the x-axis. It's an asymptote. I mean, it does eventually, but when you're asked to draw it, don't have the lines touching the x-axis at the end. And you can see that if we think of this as sort of a normal room temperature, this is all of the particles and the distribution from the coldest particles to the hottest particles, the slowest to the fastest. Most of them are kind of in the middle. If we cool that sample down, we're basically scrunching all of that towards the low energy side. So what's going to happen is we're going to move that peak up and to the left. If we heat that sample, we're scrunching it off to the higher energy side. So the peak's going to be lower, but it's going to, the tail, high energy tail is going to be higher. So that's what the differences in temperature look like on that distribution. I'm not going to skip that. When we measure transfer of heat in the context of a reaction or a system, we use this term enthalpy. We don't talk about heat as much as we talk about heat of a reaction. We talk about the enthalpy of a reaction. It's kind of the same thing, and we tend to use it interchangeably a lot of the time. Enthalpy is based on the system being at a constant pressure, and most of our reactions take place in atmospheric pressure, so we don't have to worry about the pressure part. So in those cases, changes in enthalpy and changes in heat are kind of equivalent. Enthalpy is H, and change in enthalpy is delta H, the triangle. It's going to be change in, meaning sort of final minus initial. It's the same thing when you see delta T, temperature, change in temperature from the end to minus the beginning. You can have positive changes in enthalpy or negative changes in enthalpy depending on whether reaction is coming into the reaction or heat is coming into the reaction system, absorbing heat, or if it's going out of the system. And one last thing about the delta H is that you will sometimes see a little thing that looks like a theta at the top. It's actually not a theta; it's a plimsoll, and it's basically saying that it's happening at standard conditions. But it's usually written as a theta because that's what you can write in. You can insert that character in most word processing functions, and this one is not often there. So that means that the change is being measured under standard conditions. And we're going to talk a little bit tomorrow about situations where that's going to matter, where we have data for what the enthalpy, change in enthalpy of a reaction should be under different, under standard conditions. When we're talking about a chemical reaction, we talk about whether it is absorbing heat or releasing heat, and we're talking about the reaction relative to its surroundings, the system of the reaction relative to the surroundings. It's important that you know that the system in an aqueous reaction happening in an aqueous system, the surroundings include the water. Okay, so if I am reacting to things in an aqueous system, say some acid and some base that are both dissolved in water, and I put them together and I'm measuring the change in enthalpy of that reaction, I'm measuring the temperature of the water, changes in temperature of the water, because that's most of what's in my flask. But that water is going to be, if the water gains energy, it means it gained it from the reaction, meaning the reaction lost energy. If the water goes down in temperature, that means the water lost energy to the reaction, which means the reaction gained energy from the water. So it's going to be whatever sign of your heat or your enthalpy is, it's going to be opposite between the water and the things that are dissolved in the water. So the water is part of the surroundings when we're doing a reaction in an aqueous system. This should sound familiar. We can have exothermic reactions in which energy is transferred to the surroundings. When we draw this as an energy diagram, the reactants start at a certain energy or enthalpy, and at the end, the products have less. Now, we also talked about the activation energy hump, because we just did these out of order a little bit. But the change in enthalpy between the reactants and the products is going to be negative in an exothermic reaction because the reactant started at a high energy state and ended in a lower energy state. An example of that is one of these reusable hot packs. So these are filled with a saturated solution of sodium acetate or something like that. Supersaturated solution, meaning they dissolved as much of the ions as they could into the water, and then they heated it up and shoved some more of the salt into the water until they really couldn't dissolve anymore. And then they very slowly cooled it so that it would stay in solution. So it would not come out of the solution. So this actually is a very high energy system, because there's a lot of energy keeping those ions away from each other, surrounded by water molecules. Okay? All I have to do is add a little bit of activation energy to this system in order to make the reactants go where they want to a more stable state. Now, this is not exactly a chemical reaction. It's a dissolution process, which is kind of on the border between a physical change and a chemical change. But in any case, our reactants are up here. They want to be down here. And we just need to get them over the activation energy hump. So I'm going to use this little metal thing and click it a few times to give it a little bit of energy and a place for the salt to start depositing, to nucleate and become crystalline. And hopefully this will work. Why is it not working? These are brand new, so they're a little bit tricky. There we go. So what's happening now is all of the salt is coming out of solution and creating a solid product. It is dropping to a lower, more stable energy state. All of this energy has to go somewhere, and it comes out as heat. So the same thing is happening in a reaction for the disposable hot hands, where you break it out of the plastic bag and then you shake it up in the air. That is basically a catalyzed rusting reaction. It's iron filings in the presence of some catalysts. And when you expose it to the oxygen in the air, it rusts very, very, very quickly. And that is an exothermic reaction. So that is what generates the heat for as long as you have unrusted iron filings still in the bag. The opposite, of course, is an endothermic reaction, where we start with the reactants at a lower energy state. We put energy in to make the products. If I want to take one of these and turn it back into a liquid so that I can reuse it, I have to boil it for a good chunk of time, like an hour, before it will all go back into that supersaturated solution. So I'm having to add energy into the system, positive delta H, in order to get up to the energy level of the products. Okay. All right, and this might be, yeah, we're not going to the table. Yep, this is a good time to stop. So we will pick this back up tomorrow.